So this is Chemistry 3053, and today we're going to start Chapter 8 in David Klein's book, Addition Reactions of Alkenes and also alkenes themselves. So here is what we're going to cover in this chapter: the introduction, the alkenes in nature and in industry, and we're not going to cover this much at all. Addition versus elimination. A thermodynamic perspective, and then we'll get into the part that is going to be most important to you, the actual reactions: hydrohalogenation, acid catalyzed hydration, oxymercuration, demercuration, hydroboration, oxidation, catalytic hydrogenation, halogenation and halohydrin formation, anti-dihydroxylation, syn-dihydroxylation, and oxidative cleavage. So these reactions here, 8,4 to 8,12, many of the mechanisms are going to be similar, and some will be different, and you'll have to be able to know the similarities and differences in order to be able to predict the products and to be able to predict the regiochemistry and stereochemistry of the reactions. So here are the 10 reactions again that we're going to cover: hydrohalogenation, Markovnikov and anti-Markovnikov, acid catalyzed hydration, and oxymercuration, demercuration. Notice these are grouped together because they have the same regiochemistry. Hydroboration oxidation has a different regiochemistry. Then hydrogenation, bromination, halohydrin formation, anti-dihydroxylation and syn-dihydroxylation, and ozonolysis. And so you're going to see these summaries in several different ways. Here's another summary. This shows your addition reaction. What constitutes an addition reaction is where you have two different atoms or groups added across a double bond to form two new single sigma bonds. And this shows you the type of addition reaction, addition of H and X, where H is halogen, or addition of H and OH, two hydrogens, two halogens, an alcohol functionality, a hydroxyl and a halogen, or two hydroxyl groups will be added. So we have a lot to cover here, and you'll just have to learn these reactions. So the introduction to the addition reaction. The pi bond, as you know, is electron rich. Here you have pi cloud. It's going to be outer lying. It's not going to lie in between the two atoms. It's going to be above and below the plane of the molecule. And so you have already seen how the pi bond can function as a base to attract a proton. It can also function as a nucleophile to attract an electrophile. Notice both of these reactions are drawn as reversible reactions. And once you have added one group, you're going to form a carbocation intermediate in most cases, but not in all cases. But this is a good general drawing to help you sort of understand what's going on. You will be able to understand that the addition reaction is going in the forward direction. It's the same as elimination, which you've already seen, except elimination is going in the opposite direction. Here you're adding HX, here you're losing HX, and you can actually control what which direction you have the reaction proceed in many cases. You can do it by decreasing the temperature, and you will favor addition, or if you increase the temperature, you'll favor elimination. And so that's because you have an entropy effect here. You're going towards lower entropy, and if you go in the reverse, you're increasing the entropy. So to go in the forward direction, you need a lower temperature. And if you have a lower temperature, the entropy term will be diminished, and you will favor the forward direction because you're going energetically downhill, because these two single bonds stabilize the molecule more than one pi bond, or stabilize the system more than one pi bond and one single bond. That's because a pi bond is sort of a weak bond compared to sigma bonds. And so that tells how you can favor the forward or reverse direction of the reaction. You can also favor the forward or reverse direction by adding additional HX. If you add additional HX, you can drive the reaction in the forward direction. If you remove HX, you can actually drive the reaction in the reverse direction if it is a reversible reaction. And so this more or less just gives you the actual numbers of what I already stated. So a pi bond is a relatively weak bond. You can see it's 63 here. This is 103, 101, 84. So you can see this is the weakest bond. And so this, remember that these numbers are energies of stabilization. A bond is a stabilizing entity in a molecule. So a pi bond gives less stability to this side of the reaction. So this is energetically downhill. So and also, as I mentioned earlier, you know, with regards to entropy, here this is more disordered, this is less disordered, and so going in the forward direction here, your entropy is actually decreasing. And so this addition reaction is not favored by entropy. So that's why the lower temperature favors the forward direction, higher temperature favors the reverse direction. So getting to the first of these reactions, the hydrohalogenation, addition of HX. This will be good for HCl, HBr, or HI. For hydrogen fluoride, just hydrogen fluoride, those reactions, hydrogen fluoride is just too reactive, or you know, it's just, so you're not going to see many reactions in which you actually use hydrogen fluoride or fluorine, molecular fluorine. And so here you can see that the HBr is added across the pi bond. Here you've got the hydrogen added to one side, bromine added to the other side. You're not looking at regiochemistry here because this molecule is symmetrical. But if it's not symmetrical, two regioisomers are possible depending on where the proton goes, because the first step is going to be protonation. Anytime you have an organic molecule in the presence of an acid and a reaction takes place, your first step is always going to be protonation. Let me say that again. Anytime you have an organic molecule in the presence of an acid reacting with an acid, the first step is always going to be protonation. So your question has to be, where will the proton go? Because whichever side the proton goes to, the halogen or the anion is going to go to the other carbon, right? Because you can't put them both on the same carbon. So once you've decided where the proton goes, you've automatically decided where X goes, because it has to go to the other carbon. So the first thing that you have to look at is to decide, where does X go? So wherever X goes, the other carbon is going to bear a positive charge, right? If hydrogen goes here, this carbon will bear a positive charge. If the proton goes here, that carbon will bear a positive charge. So where do you want the positive charge? You want the positive charge to go where you will have the more stable carbocation. So you will put the proton here and the plus charge there, and that will be your intermediate. And that means in the next step, X will have to go where the plus charge is. Okay, so you're going to see that now again and again and again. So the hydrohalogenation is regioselective for Markovnikov addition. And so that the regioselective means that one of the two products will be favored, but not entirely favored. In other words, you won't get 100% of one product. You'll get a predomination of one product. So you have two possible products here where hydrogen can go here or here. One will predominate, only one. You'll get a little bit of the other one, so it's called regioselective because you'll have a major and a minor product. So where is the proton going to be attached? It's going to be attached to the less substituted carbon, because the more substituted carbon will be able to bear the positive charge better. You'll have a more stable carbocation if the positive charge goes here. And once the positive charge goes there, then you're going to be left with Br minus, and it will attack where the positive charge is. So your decision about where the proton goes automatically determines where the bromide will attack. It will attack at the other carbon. They can't both go to the same carbon. Okay? So, now this is giving you a little preview. We're not going to discuss this much at all, except whenever you have peroxides, RO, OR, two oxygens bonded together, that's a peroxide. When you have the presence of that, you get an entirely different mechanism. I'm not going to go into the mechanism now, but it's an entirely different mechanism, and you will get the opposite regiochemistry, and that's called anti-Markovnikov addition. What you just saw in the previous transparency is Markovnikov addition. If you have peroxides, it gives you the opposite, anti-Markovnikov addition. We're not going to go into that much because you're going to get that in a future chapter. Okay, you'll get that in chapter 10 after we cover both alkenes and alkynes. So we're not going to discuss it here. We're going to go into it in detail later on. So now let's look at this comparison again. So if you add HBr across the double bond, you get Markovnikov addition. The proton attacks, or it becomes attached to the carbon that is less functionalized, less substituted, because the positive charge is more stable at the more substituted carbon. And then once you have the positive charge here, the Br minus comes in and attacks where the positive charge is. That's the mechanism whenever you have an acid protonating the alkene. This is and you have Markovnikov addition. This is an entirely different mechanism. It's an entirely different mechanism. Okay, you do not get the proton attacking as the first step, or the attack on the proton is the first step, or the attachment of the proton on the first step. Down here, it's an entirely different mechanism, so don't get them confused. When you see the peroxide, it's an entirely different mechanism. Okay? So now, here is the mechanism I've been talking about. So, the first step is attack on the proton, and then bromide departs bearing a negative charge because it takes with it this pair of electrons. So the alkene, the double bond, is protonated. Here it is. Which end of the double bond does the proton go to? It goes to the end so that the other carbon is more stable, bearing the positive charge. So this is the more stable carbocation. If you had put the positive charge here, you would only have a secondary carbocation. This way you have a tertiary carbocation. This is the more stable of the two possible carbocations that could be formed. And so then once you have this determined where the proton will go, the bromide has to go here. It can't go anyplace else. So the important step, the step that determines the regiochemistry, is the first step, the attack on the proton. Where does the proton go? That you have to remember that. It's the first step, the proton transfer. That's what is important. That determines the regiochemistry. Now, here is the energy of activation up to the transition state structure up here. So the energy of activation is the energy difference between the reactants and the energy of the transition state structure. So you can see this is the higher energy hill. You go down to a high energy intermediate, then you go across another, go through another transition state structure over another energy hill, and then down to the products. And you can see that the products are more stable than the reactants, as I mentioned earlier, because the double bond here, the pi bond, is relatively weak compared to single bonds, sigma bonds. And so you're going downhill in energy as the reaction takes place. This is the rate determining step, right? The protonation to go uphill to the high energy reactive intermediate. This is a high energy reactive intermediate. So you're going to go over the energy hill, the rate determining step. The rate determining step, when you have a reaction that where the first step is going to a high energy reactive intermediate, the first step is going to be rate determining because it takes energy to get uphill to go to that reactive intermediate. Now, so there are two possible products. One, remember, this is the anti-Markovnikov pathway, and so you could theoretically have a proton attached at this tertiary carbon. You could have a secondary carbocation formed. This would be the anti-Markovnikov product because this is going through the less stable intermediate. This one is going through the more stable carbocation intermediate, and so this is the Markovnikov pathway, where the proton becomes attached so that you form the more stable carbocation intermediate. And the product that results from this intermediate is going to be the major product. You will have some of this, but much less. And sometimes it will be a considerable amount, like 30%. Sometimes it'll be a tiny amount, like 2%. It will depend very much on the reaction. So this is another way of looking at it. This is the same reaction we were looking at, and this is going through the higher energy transition state to give you the secondary carbocation. This is going through the transition state structure that leads to the tertiary carbocation. So this is the situation that I have mentioned many, many times before, where the higher energy transition state structure corresponds to the higher energy intermediate and the higher energy product, and the lower energy transition state structure corresponds to the lower energy intermediate. Okay, so this is what I would call the normal situation. And you can see that since this is going through a higher energy transition state, this reaction is going to have a higher energy of activation compared to this, where you're going to have a lower energy of activation because you're comparing it against the energy of the reactants. So the energy distance going here to the higher energy transition state structure is more than the energy distance going to the lower energy structure. And so it's going to be easier to get over this lower energy hill, and it will be harder to get over this higher energy barrier. So that's just sort of common sense. So the reaction that leads to, back up, the reaction that leads to the more stable carbocation is going to have a faster rate. It will be a faster reaction. So now, hydrohalogenation may result in the formation of a chirality center, as you can see here. So here it's shown without any stereochemistry. When it's drawn like this, it means that there are actually two enantiomers in equal amounts. This is showing that you do not have optical activity as it's drawn. This is what this would mean. It doesn't mean that you have the R configuration or the S configuration. It means you have a 50-50 mixture of R and S, unless it states otherwise. And why do you have a 50-50 mix of R and S? It's because you've gone through a carbocation, and a carbocation is a planar intermediate. So here is your planar carbocation. And so when your nucleophile, the anion, comes into attack, it can come into attack from the top or from the bottom, and it'll be a 50-50 mix. So you're going to have an equal amounts of your two enantiomers. And so you would not get any optical activity from that reaction. So remember, another thing that we've talked about carbocations before is that when you have a carbocation formed, here you're going to protonate. Where will you protonate? You'll protonate at the end so that you'll have a secondary carbocation formed. And now, since you have this branching next door, you have the possibility of a 1,2 hydride shift. And so now, after that happens, you have a tertiary carbocation formed, and then the nucleophile will come in and attack at the tertiary carbon. And so you can see immediately that you had a rearrangement of some sort because the chloride is not becoming attached to either of the carbons that were originally involved in the double bond. The chloride is becoming attached over here. And so you will have to remember that you can have a 1,2 hydride shift. The methyls won't migrate because a hydride will migrate preferentially to a methyl. So you can have acid catalyzed hydration. The water H and OH instead of H and X will add across the double bond, but the mechanism is the same. The mechanism is exactly the same. And it's important for you to recognize that these mechanisms are the same, because then you don't have to learn a bunch of different mechanisms. You learn one mechanism, and you can learn how many different reactions fit that one mechanism. And it makes the whole thing a lot easier to learn. And so, again, what happens is you have an acid, and the first step, when an organic molecule reacts with an acid, and this just has, it can have just a little bit of acid in it. So the first step is going to be protonation of the organic molecule. And you have to look to see, what's going to be the most reactive of your functional groups. You only have one functional group here, so that's going to be the functional group that's protonated. So here you will protonate this double bond, and once again, as we just went over repeatedly, the proton will be attached to the carbon that gives you the more stable carbocation, and that's going to be at the tertiary carbon. And so then once that bond once the positive charge is generated at a tertiary carbon, oxygen will come in and react because That's the only reactive place at that point. Once the proton is attached, then oxygen automatically has to go to the other carbon. So this really is just the same mechanism that you've already seen. So this is really just sort of repetitious. So once again, we're going to have the proton come in and be attached. It will be attached to the double bond. Here it will be attached to the double bond. Here it will be attached to the double bond. It will be attached in a manner such that the more stable carbocation will be formed. Here it doesn't matter, they're equal. Here the more stable carbocation will be at the, to form a secondary carbocation. The proton will be out here. This is where the more stable carbocation will be, and here, this is where the more stable carbocation will be. And wherever the more stable carbocation will be, that's where the oxygen will attack. And so you can see that this is going to be a primary carbocation, this is going to be a secondary carbocation, this is going to be a tertiary carbocation, and the stabilities of those carbocations will influence the height of the energy barrier in each one, and so this is going to have the lowest energy barrier, and therefore this will have the fastest rate. Okay, and that corresponds to the lower energy barrier and the more stable carbocation. Okay, so once again, this is just drawing what I just said. You protonate the double bond in a manner such that you get the more stable carbocation, and then that is where the oxygen comes in and attacks. Once you attach the proton, the oxygen, the site of oxygen attack is fixed. So it's whichever carbon attacks the proton or becomes attached to the proton, that determines where oxygen will attack at the other carbon. Now, this is going to get a little bit of nomenclature, which is going to be a little bit important. And here we're talking about oxonium ion. So the oxonium ion, here you can see it's oxygen bearing a positive charge. You actually had an oxonium ion here also. This is an oxonium ion. It is simply an oxygen bearing a positive charge. Now, oxonium is a type of onium ion. And an onium ion, by definition, is an ion in which an atom has increased its valency by 1, or has a valency which is 1 higher than normal. So normally oxygen has a valence of 2. It's divalent. Okay? And here you can see this is 3. It's trivalent. It's bonded to 3 different atoms. And it is bearing a positive charge. And so when an atom has increased its valence by 1 and it's bearing a positive charge, it is an onium ion. And the oxonium tells you that it's an oxygen onium ion. So this is an oxonium ion. And you're familiar with some of these things. I mean, you're familiar with ammonium ion. If you'll think about it, that is NH4 plus. And you are very familiar with that. And that is an onium ion because the nitrogen has increased its valence by 1. It's like NH4 instead of NH3. And it's bearing a positive charge. So that is probably the most familiar example of an onium ion. But you're going to see others in this chapter. You're going to see bromonium ions, chloronium ion, and mercuronium ion. And there are many, many others. And so you need to get this concept in your mind, the definition. I don't think it's clearly given in the chapter, but I just gave it to you. It is a case in which an atom has increased its valence by one more than its regular, what is normal for it, and it's bearing a positive charge. Okay? So let's go on, and we'll see these. I will point them out to you as they go along. So here, once you have this oxonium ion, you need the neutral molecule. The neutral molecule is what's going to be stable, and so something has to come in and pluck off a proton. And so it can be water, it can be the solvent, it could be a molecule of alkene, but something needs to pluck off that proton so that you can have the neutral product formed. And so these are in equilibrium. So here you've got some acid. You would protonate this. You're going to protonate it at the less substituted carbon, so you will have the positive charge generated at the more substituted carbon, and then that's where the oxygen would come in and attack. And so you can control this equilibrium. If you want to push the equilibrium towards product, you would simply add more water and you'll push it towards the product. If you want to effect the opposite reaction, you could simply remove water by adding molecular sieves or by distilling off the water. You could so you can make the reaction go forwards or backwards. The stereochemistry is the same as I mentioned to you earlier. Anytime that you go through a reaction, anytime you affect a reaction that goes through a carbocation intermediate, you're going to form both enantiomers as products. So this is really just the same as what you saw earlier. If it goes through the carbocation intermediate, the carbocation is going to be planar, and then when the nucleophile comes into attack, it will attack and with equal probability from the top and bottom, and you're going to have a 50-50 mix. And usually the two enantiomers will not be drawn out like this. This is a little bit unusual to have them drawn out. People usually just don't bother if you have both enantiomers formed in equal amounts. So that takes care of the first part of this chapter, and in the next video we will cover some more of these reactions and mechanisms.